G'day, it's Mr. Kane here again, and welcome to a video all about the light and the rules that it goes by. So light does a few things. It either bounces off stuff, we get reflection, or it goes through stuff and we get refraction. So we're going to look at how it behaves with those things. So we're going to look at sort of the laws that light has, because it does behave by certain rules. This is probably the key rule. The angle of incidence equals the angle of reflection. Okay, so however it comes in is the same as the way it goes out. But that does rely on about a certain thing called the normal. We're measuring the angle of incidence to a thing called the normal line. And here on my diagram, this is the normal line here. And it is at right angles, oops, not really the right angle sign, to the reflecting surface, to the mirror here. Okay, so the normal line is at right angles. Now that is for every incident ray, so every ray that's coming in, the normal line applies to that ray and then the reflected ray comes out. If I have another incident ray over here and then a reflected ray coming out, their normal line is at the point where they meet the mirror at right angles there. Okay. So the angle of incidence equals the angle of reflection when measured from the normal line. That's the key part to it. Measure it from the normal line at the point where it hits the reflecting surface. This will become clearer later on. So, two kinds of reflection. There's what they call the specular, or your reflection in a mirror. It's regular, you can see what's going on, you can see a picture, you can see yourself. Diffuse reflection. That's what you get off a sheet of white paper, for example. The surface is rough, so the light rays coming in, they're coming in regular, but they're being scattered. So in a specular reflection, they're coming in a regular fashion, being bounced out in a regular fashion. Diffuse, they're coming in regular, but as you can see, they're going out in all different directions. So smooth surfaces reflect in a regular fashion. If it's a rough surface, it's a diffuse reflection because it goes in all directions. Then we get curved mirrors. Here's a classic spoon image, the inside of the bowl and the outside of the bowl, giving two completely sort of different images, same image but quite different, as you can see. So what goes on in what we call convex and concave mirrors. So we'll start with concave, and that's the one that goes in. We always get told concave, a cave goes in, a concave mirror goes in. So what key things are we looking at? Okay, concave mirror, the rays that come in, the parallel light rays that come in, always go to a single point. Okay, they always come to a single point. Wherever they come in from, hit the mirror, they always goes through that one point. That's called the focus point. And it's in front of the mirror. And that leads to some quite useful things with concave mirrors. Here's a solar oven. So we've got the big curved mirror. Okay, where's my pen gone? Big curved mirror here. Okay, big curved mirror. And sitting at the focal point right here in the middle is a pot of water. So all the light rays coming in are being bounced to that pot. Wherever they're coming in from, the light rays are reflected off the mirror to that pot. So all the energy from the sun is going to that pot. Here's something else a little bit unusual about concave mirrors. With the solar oven, all the light was coming in and going to the focus point. Well, here's a headlight from a car. If the light starts at the focus point, it's going to go out in all directions and then go out in a parallel beam. So wherever it comes out from the light, it's going out in a parallel beam to create your headlight beam. So if light comes in to a concave mirror, it's all going to go through the focus point. If light starts at the focus point, it's all going to go out as a parallel beam. Now when we come back to our laws of reflection, the incident ray, okay, coming in is equal to the angle of the reflected ray when measured from the normal line at this point. So at this point, the normal line is at right angles to the mirror at that point. This light ray coming in and this one coming out have their own normal line here. So each light ray coming in has its own normal line. So for every mirror, for every light ray, they have their own normal line. So the rule still applies. The incident ray and the reflected ray have the same angle as measured from the normal line. Concave mirrors, same thing going on. Incident ray's angle to the normal is equal to the reflected ray, but it's a diverging mirror. In this case, the rays spread apart. They come in, hit the mirror, and spread out. It's as if the focus is behind the mirror, and they spread out from there. Okay. And how do we use these? Well, you might have seen these in shops to give you a wide field of view so you can see all corners of the shops. And some people like to do sneaky things behind shelves and stick things in pockets. Well, these mirrors help us stop that from happening. And another place you'll commonly find these diverging mirrors is on the wing mirrors of cars. It's slightly curved to give you a wider field of view. However, there's often a warning written on the mirror that objects are not quite as close as they seem to be. Okay, to be aware of that. The next thing that light does is it refracts. That's bending. So they change speed. They go into something more dense, so there's the stuff more closer together. It slows down, so glass or water. If they leave them and go into a less dense medium, like going into the air or into space, they speed up. Just like us, if we're running through the, down the beach through the air, we're going quite fast. When we hit the water, we slow down. It's a more dense medium. Light does the same thing. So if we're going from air to water, from less dense to more dense, it's going to slow down. So the speed decreases and it bends towards the normal line. There's our picture there. So we've got the normal line, which is at right angles to the water surface in this case. So right angles there, you can see it. And the light coming in, and then it bends towards it. So we're bending towards the normal line. The reverse happens when going from water to the air, or from a more dense to a less dense medium. Okay, speeds increases, it bends away from the normal. There's our normal line, right angles to the surface again. Okay, right angles to the surface. Here's the light ray coming out, and then it bends away. So here we go, away from the normal line because it's speeding up. So how do we make use of that? Well, let's see what happens first. Something's a refraction of water, straws look bent. You get some funny pictures looking at things above and below the water. And here's one of my favourite refraction shots, the hole in the bottle. All done carefully with the water and wine glasses and refracting or bending of the light rays. Is there really a hole in that bottle? This is how fish appear to us when we're looking at them in the water. In the reality, they're a bit deeper than where we see them. So if you're actually hunting fish with a bow and arrow, like they do not far from where I live, there's a competition where they hunt fish with a bow and arrow, you have to adjust for the refraction of the light rays. If you're a kingfisher, the bird that catches fish from the water, it gets very good at knowing where the fish is, otherwise it goes hungry. So where the object is, apparently it changes due to the way the light waves bend as they go from water to the air. So how do we apply that? So let's say we've got a thing called a lens. Okay, it's a curved piece of glass. The light comes in, there's our normal line, it refracts towards it, comes out, there's a new normal line the way out, bends away from that. So if we apply several of these, they all come to a point and we can use it to adjust the focus point in our eyes. The glasses I'm wearing help me with close-up vision because as I'm getting older, the muscles that control my eyes are getting a bit worn out, so I need some help to focus the light in the right place in my eye. Some people like that are from the day they're born. Their eyes are just not quite the right shape, so they have lenses in front of them, which means the light is focused onto the correct part of the eye so they can see and focus in clearly. So, lenses, glasses. So, I was getting frustrated with reading. I was finding it hard to read. Then I got glasses and just made life so much easier, so much more relaxing. I actually enjoy putting on my glasses now when I'm able to read. Magnifying glasses make things bigger, so we can actually see more detail. You can use those in a single hand lens or microscopes. Binoculars, combinations of lenses. Telescopes, more combinations of lenses. And microscopes. And here comes the question for the end of the video. If something's transparent, as light passes through it, how do you actually see something that is transparent? Okay, hope that's all good and we learnt something through that video, and we can replay it and look at it again if you need to double check on something. Thank you.